Our next topic is a system of first-order linear ODEs. It's a system of equations, except that now those equations are all first-order ODEs that are on the top linear. So this is a general definition of what this object is, right? So in this case, you have n equations. They're all first-order equations that are solved for derivatives of your known functions, x1 prime, x2 prime, and so on. And each derivative is a linear combination of all of the unknown functions. So for example, x1 prime is a linear combination of functions x1 through xn with coefficients that can in principle depend on an independent variable t. And then each equation also has f1, which is a function which is independent of x but dependent on t. And so you have n equations like that, n equations with n unknowns we should be able to solve, which we eventually will be able to do. So one important comment here is that if all the coefficients, all the functions f are equal to 0, then we say that the system is homogeneous. And otherwise, if at least one of f's is not 0, then the system is non-homogeneous. Let me give you a couple of examples. So this is an example of a 3x3 homogeneous system. 3x3 in this case means you have three equations with three unknowns. Three unknowns are x1, x2, and x3. And you see that each equation looks like a linear combination of these functions, x1, x2, and x3, with coefficients that depend on time, right? Plus some additional function, known function here. So each equation looks like that. So that means that you have a 3x3 non-homogeneous system. Next, we have a system of two equations with two unknowns. So that's a 2x2 system. Again, both equations are first-order linear ODEs. And this is a homogeneous system because there is no f here, right? No additional function that we added here that depends on t. And by the way, these are ODEs with constant coefficients, right? Non-constant coefficients in the first example. Now let's see whether this does or doesn't have a physical relevance. We can do our usual example with springs. So unlike the situations that we considered previously, where we had one spring with a mass, let's suppose that I have two springs. Now I'm going to assume that these springs and masses have the following configuration that I have shown in this picture. So I have spring 1 attached to a wall, then there is a mass attached to that spring, second spring attached to the first mass, and then another mass is attached to at another end of spring 2. And I'm going to make a bunch of assumptions here. So I would assume that there is a spring constant K1 in the first spring, maybe a different constant K2 in the second spring, that there is a friction between the mass and the floor or the table, whatever this system is, friction with a coefficient gamma 1 for the first mass, and another possibly different friction with the coefficient gamma 2 for the second mass. And then another assumption that I'm going to make is that M1 and M2 are really tiny, so that both masses are super light, so that M1 and M2 effectively I can assume to be 0. If that is the case, and if I denote the displacement of the first mass or elongation of the first spring by x1 of t, and elongation of a second spring by x2 of t, then I can try to write down the second Newton's law for both masses. And let's see what we're going to get. So this is a second Newton's law in which I assume that the mass is tiny, that both masses are tiny. So mx double dot, mass times acceleration term, is just equal to 0. And so what I would see is that there is a balance of forces onto m1 and balance of forces on the mass, on an object m2. And what are the forces? On m1, I have force, a friction force, which is typically written as gamma times the velocity, right? Gamma 1 times the velocity of the first mass. And that friction force has to be balanced by forces due to springs. There is a typical force in a spring 1, right? Minus kx1. And then there is a spring force in a spring 2 that also acts upon the mass m1, but it acts upon it in a different direction, right? If the spring 2 is elongated, then the mass will move in a positive direction. And so we have the first version of second Newton's law, except that because the mass is 0, mass 1 is 0, then there is no second derivative here, right? And a similar balance should hold for the object 2. Again, m2 is equal to 0, so there is no second derivative term. And there are two forces. One force is friction, and the second force is due to the forces generated by elongation of a spring 2. Force due to friction, right? What is the velocity of m2 or displacement of m2? It's a sum of displacements of elongations of spring 1 and spring 2, so it should be x1 plus x2. So velocity of m2 is time derivative of x1 plus x2. Times the friction coefficient, this gives me a friction force. And then mass due to spring is just minus k2x2 as always. So what I already got is a system of two first order ODEs, right? It doesn't yet look like the system example of a system that I written above, because those were solved for x1 dot and x2 dot. So let's try to do this. I can solve the first equation for x1 dot simply by dividing by gamma 1, right? Take this equation, divide by gamma 1, you get this guy. Take a second equation, divide by gamma 2, and then you get on the left side x1 dot plus x2 dot, and subtract x2 dot from both, x1 dot from both sides, and you end up with a second equation like this. Then I can take x1 dot from the first equation and replace x1 dot in the second equation by this expression. And when I do that, I end up with a system, 2x2 system of linear homogeneous equations, right? Because there are no additional functions added to either of the two equations. So it's a system of 2x2 system of homogeneous equations. Now, in this case also, if I want to find the positions of masses at any moment of time, I need to prescribe initial conditions. So in this case, I need two initial conditions because I have two first order equations. So prescribing initial position of a mass 1 and initial position of a mass 2 should do. And so we get a second order initial value problem, right? So the system of two ODEs subject to initial conditions. So the structure is very similar to what we have seen before, except that we have to deal with two ODEs that are coupled, right? That I have to know both x1 and x2 to find x1 dot and x2 dot, right? I cannot just solve equation for x1, ODE for x1 and ODE for x2. Those are coupled here. And as we will see momentarily, actually, the theory for these systems actually is very similar to the theory that we studied for single linear homogeneous, for that matter, ODEs, because I'm only going to discuss homogeneous ODEs in a sequel. And it actually might be worthwhile to try to rewrite these systems, right? It's a pretty ugly expression, this general linear first order system, right? It's a fairly large expression. So we probably can benefit from writing it in a simpler, more compact way. And to this end, I'm going to remind you about matrices, right? So the matrix is an n by n matrix is going to be a table of n square numbers like this. A vector in Rn we can write using our typical notation, right, as x1 comma x2 written in a row, but you can also write it as a column instead. And when the vector is written in this way, then it would be easy to define a product of a matrix and a vector in the following way. So if I look at a matrix, one row of a matrix will have n entries in it. So I can treat this row as a vector. So it's a vector in Rn with n components. My vector x is also a vector in Rn with n components. So I can take this vector and take a dot product of this vector with that vector. That will give me a number. So this dot product is going to look like this, right? So component-wise product of the first row and my vector column gives me a number. Then I can do the same thing for the second row, same thing for the third row, etc. And lastly, I'll do this with the nth row. Nth row, again, is a vector in Rn, right? Vector with n components. And I can take a dot product of that vector with my vector x in the usual way, again, as a component-wise product and then a sum, right? So the first component of this row is an1. I'm multiplying it by x1. Next one that I have not written here is an2, right? Because the first index here will stand for the row, and the last index stands for the column. So nth row will have a first index equal to n. Again, the first component is an1, second component is an2. So x1 should be multiplied by an1, x2 by an2, right? And that's what we got here. And you keep adding until you multiply the last component here with xn, and that's what you got there. Because you have n rows in the original matrix, this product of A with X would also have n rows. So we started with a vector in Rn, the column which had n rows, and we ended up with a vector in Rn, a single column, which has n rows, but those are written in a more complicated way now. Now, when you have a vector function, you might remember from Calc 3 that to take a derivative of a vector function, you simply take derivative of each component. And then I can also introduce another vector, column vector f, which will have components f1, f2, etc. So now with this definition, let's see how we can write this system in a simple way. Well, the derivatives are basically derivative of a vector x, right? Which consists of components x1, x2, x3, etc. up to xn. So this derivative I can write as x prime. F's I can write as a vector f. And then if I compare what I got as rows in my matrix vector product AX, I see exactly the same things as I see on the right hand sides of ODEs in my system, right? So the first linear combination is A11x1, A12x2, ends with A1 and xn, and that's exactly the same thing as what you see here. It will be the same for all equations. And so by using this matrix vector notation, matrix vector product in particular, I can write my equation in a matrix form or in a vector form, and it will look like this, right? So now it looks much simpler. So now if we go back to the examples that I showed you before, so the this first original system, right? If we think about it, the vector f must be the sine, cosine, and minus square root of t. X prime is a vector which has three components. And then the matrix A of coefficients will be dictated by t, 2, t squared, etc. So basically the matrix is just composed of these coefficients. And so one thing that I'm missing here is a minus sign. So f, like I said before, is in this first case is this vector of three functions, and then if you compare to the example above, this would be a matrix A of coefficients. In a second example, we had 2 by 2 system, so we have a vector with two components. And then the matrix just looks like, what, 2, 3, minus 1, 1. And that's exactly what I got here, right? 2, 3, minus 1, 1. And that was a homogeneous system. So there is no vector f associated with it. And finally, my spring example, I can again write as a vector equation where x has two components. And A is going to be a matrix of constant matrix that looks like this. And the initial condition is going to also be a vector initial condition because I prescribe both initial position of a mass 1 and position of a mass 2. So the initial value problem also is written in a much simpler way, similar to what we have written before, except that now the meaning of x in this equation is that x is a vector and A is not a constant anymore. A is a matrix. And the product that you're taking, AX, is this matrix vector product. And a final comment here is that, so if I see a system like this or matrix equation like that with capital F, then it's non-homogeneous. If there is no capital F, then it is homogeneous. Okay, so now let's do a couple of examples here. So let's say I have an equation, this matrix equation, x prime equal to a matrix 2, 1, minus 1, 0 times x. And I want to verify that both this function and this vector function are solutions of this equation. So how do I do that? I'll do this in the usual way. I need to substitute and make sure that the equation is satisfied. So let's look at x1. It's a scalar function times a vector plus another scalar function times another vector. How do you combine those, right? So if you multiply a vector by a scalar, you have to multiply each component by that scalar. And if you add two vectors, you add their respective components. So e to the t, 3e to the t are going to be components over here. And 4t e to the t minus 4t e to the t will be a second vector. And you add them together, and that is your x1. So then to find x1 prime, you have to differentiate both entries. So you differentiate this, you get that. You differentiate the second component, you get the expression here. You simplify, and you end up with this vector. Right, again, vector because it has two components. And to check that the equation actually is satisfied, the next thing that I need to do, I need to multiply the matrix that I have here by this x1 and verify that I'm going to get the same vector as x prime. So we're doing matrix vector multiplication. So I take vector 2, 1, and I take a dot product with my vector. So it's 2 times first component plus 1 times the second component. Right, that would be my first entry. And the second entry minus 1 times the first component plus 0 times the second component. Very good to have 0 because then the only thing that you have is minus 1 times the first component. And that's what you have here. All right, and then now you simplify and you end up with exactly the same thing as before, as x prime. So that means that x1 is a solution of this equation. Now you do the same thing for x2. You take x2, take its derivative, nothing changes because it's just exponentials. And then ax2 ends up being exactly the same, so x2 also is a solution. Fine. Remember what we had for, one thing that we had for linear ODEs, homogeneous linear ODEs. There are solutions satisfied the superposition principle. If I take a linear combination of solutions, so if I have a bunch of solutions, x1 through xk, multiply them by constants, add them together, then the outcome still solves the original equation. And this can be shown in exactly the same, to be true in exactly the same way here. That exactly the same property holds. That if I have a bunch of solutions of my matrix equation and I add them together with arbitrary coefficients, then the result is also a solution of the same equation. So I shown this here for 2x2 systems. I'm going to skip talking about it. I will just encourage you to look at this proof. And it's not actually a proof, it's a verification that actually, in the case of 2x2 systems, the superposition principle holds. And you can do exactly the same, make exactly the same argument for systems of a larger size. Okay, so superposition principle is true. The next thing that we discussed for systems, for ODEs, for regular ODEs, was the notion of linear independence. So there it was notion of linear independence of functions, of scalar functions. Now it should be a notion of linear independence of vector-valued functions. In fact, you can talk about linear independence of just vectors that are independent of time. And let's talk about that for a moment. And the definition is exactly the same as before. A bunch of vectors is going to be linear independent if whenever you construct their linear combination and set it equal to 0, the only way for that linear combination to be 0 is if all coefficients are equal to 0. And if not, then if at least one of those coefficients is not equal to 0, then vectors are going to be dependent. And just like before, the dependence will mean that if I have one vector, if I have a system of vectors, of k vectors, set of k vectors that is linearly dependent, I will always be able to express one vector as a linear combination of other vectors. Okay, so to this end, a couple of examples again. If I have two vectors 1, 2, and 2, 3, are they linearly independent or not? I can just verify this statement that I've written here. So let's say I have C1 times 1, 2 times the first vector plus C2 times the second vector. This is equal to a 0 vector. What does it mean about C1 and C2? So actually this gives me a system of two equations with two unknowns, C1 and C2, right, by just adding vectors together. So C1 plus 2C2 is equal to 0, 2C2 plus 3C2 equal to 2C1 plus 3C2 equal to 0. By solving this system, you quickly find that C2 and C1 both must be equal to 0. So that means that vectors are linearly independent. And if they were dependent, then one vector will be a scalar multiple of another. And obviously that is not the case here, because if one vector is a scalar multiple of another, we must have the same direction, as you remember from Calc 3. And certainly that's not the case here, right? 1, 2, and 2, 3 are not pointing in the same direction. We can ask the same question for free vectors in 3D, will those be linearly independent or not? So one way to do it is to demonstrate if they're independent or not would be to, once again, solve the equation C1 vector 1 plus C2 vector 2 plus C3 vector 3 equal to 0, and show if C1 and C2 and C3 are 0 or not. But in this case, actually, you can show by inspection that the third vector is 3 times the first vector plus twice the second vector. So third vector is a linear combination of the other two, and so that means that the system of this set of 3 vectors is linearly dependent. Okay, but our goal actually is not to talk about the vectors per se, but what we want to know is whether or not the n vector functions that you got are linearly independent or not, just in the same way as it was the case for solutions of ODEs. And the checking is done in exactly the same way as before by computing a Vronskin. Except that now, right, remember before, the Vronskin was, it contained function and its derivatives. And in this case, the Vronskin just contains the function. So if I have n vector functions, right, x1 through xn, and let's suppose x1 has components x11, x12, etc., x1n, x2 has components x21, right? So again, x's are represented by columns, my vectors are represented by columns. So if I have n vectors, I have n columns, they're all in Rn, so they also have n components. So I get a determinant which has n rows and n columns, and the functions x1 through xn, or n solutions of your system of equations, are going to be linearly independent if the Vronskin is not equal to 0. So going back to that example that I did previously, remember that we showed that these two guys were two solutions of a linear equation, linear system of ODEs, or a matrix equation up here, right? So that was this example. And so now I want to demonstrate that the same two functions are linearly independent. How would I do that? I have to construct a Vronskin. So if I combine everything here into one vector, just like I did before, and if I write this also as a vector, right, I can distribute, if I multiply a vector by a scalar e to the t, and then I get to multiply all components, minus 1, 1, 1, and minus 1 by e to the t, so that's your x2. So you construct a Vronskin out of these two columns, right, vector columns. This would be a first column. This guy gives you a second column. So this gives you a 2 by 2 determinant. You compute this 2 by 2 determinant in a usual way, and you end up with minus 4 e to the 2t. Exponential is never 0, so Vronskin is never 0. So that means that x1 and x2 are linearly independent. And so what you got then is a system of two equations, right, with two unknowns that I wrote up here, right? So two equations with two unknowns, x1 and x2, or a single unknown vector in 2D in R2. And you want to find the solution. So if it is a system of two equations of the first order, so then I have to integrate each equation once to get the solution. So there should be two unknown constants that are involved. And so if a linear combination of two solutions will give me, for the linear combination of two solutions to give me a general solution which contains two unknown constants. Again, I'm referring to what we did for a single ODE because it's exactly the same here. I need to know two linearly independent solutions of that equation. So if you have an n by n system, x prime equal to ax, right? How do I construct its general solution? If I do know n solutions, then I can write c1x1 plus c2x2 plus etc. plus cnxn, and by superposition principle, that guy is going to be a solution of my equation and will have n unknown constants, right? In 2 by 2 case, I'll need two constants. In n by n case, because I took first derivative of n x's, I need n constants. But to make sure that those solutions are actually different, those n solutions that I list here are different, I have to verify their linear independence. So if they're linearly independent, then again, just like before, they form a fundamental set of solutions, and their linear combination is going to be the general solution. And so we already verified that for this system, I have two solutions, x1 and x2. They're linearly independent, so that means that the general solution is going to be a linear combination like this. So in order to solve then an n by n system of linear equations, a homogeneous system, what I will need to do, I will need to find n linearly independent solutions, vector solutions like this. So the theory is really exactly the same as before, except that again, the objects are not scalar functions, but vector functions. And then we can solve initial value problems, right? So if I want to solve now initial value problem for this equation, and I prescribe some initial conditions, then I already know the general solution, and I just need to figure out the constants. And for that, you substitute, right? So x of 0, you know, is 1, 2. You substitute 0 into x of t. You end up with that. You simplify. So you get the sum of two vectors, constant vectors, with unknown constants. You combine the vectors, you equate the corresponding components, and you end up with a system of two, now just algebraic equations with two unknowns, which you can solve, and you find that C1 is 3/4 and C2 is 1/4. And so you plug those back into the expression for x of t, you get something like this, and then you simplify, and you get the final solution that looks, that has this form. All right. So the last comment that I'm going to make here is this, last comment in this lecture. That in fact, actually, you can show that linear homogeneous systems are equivalent to higher order linear homogeneous equations. And I'm just going to demonstrate it by using two examples. The first example is going to be, I'll take a second order linear homogeneous equation, and I can show that this equation is equivalent to a system of two first order ODEs. And then I'll take a system of two first order ODEs, and I'll show that it is equivalent to solving a second order linear homogeneous equation. So let's say we have a second order linear homogeneous equation like this, and I'm going to define two new functions. Y1 is going to be a different notation for y, right, the solution of this ODE, and y2 is going to be y prime. But if y2 is y prime, right, I now call y y1, so that means that y1 prime is y2. Okay, so if y2 is defined as being y prime, if I take the derivative here of both sides, I'll get that y double prime is y2 prime. And then I can go back and replace the derivatives in my ODE, but what I know about y2, right? So y double prime is y2 prime, y prime is y2, and so my equation now looks like this. right? And the y is replaced by y1. All right, but then what I got now is two first-order ODEs. One first-order ODE for y1 and a second first-order ODE for y2. If I move everything on the right side, on the left side to the right side, except for the derivative in this equation, then I get this for y2 prime. I get, I'm just rewriting this equation for y1 prime, and that is a 2 by 2 system, right? Which if I wanted to, I can write in a vector matrix form. Okay, so if I have an ODE, second order linear homogeneous ODE, I can write it as a system of two first order ODEs. Let's try to do this backwards. Now let's suppose that I have the system that I already discussed above, right? A system of two first order homogeneous ODEs with constant coefficients, in fact. And I want to see if I will be able to eliminate one of the functions from here. So this matrix vector form of the equation I can just rewrite as a system of equations, right? X1 prime by working with components of my equation, I get a system of two ODEs. And out of this system, I'm going to try to eliminate x1. And the way I'm going to do it is I'm going to take the first equation and I'm going to take its derivative. I'm going to take the second equation, not the first equation. I could do this with the first equation too, but let's do it with the second equation. Take the second equation and take its derivative with respect to t. And keep the first equation the same. So the first equation is unchanged, and the second equation now becomes x2 double prime equal to minus x1 prime, right? Derivative of the right side is equal to derivative of the left side. Well, but then keep x2 double prime, and if I look on the right side, I have minus x1 prime, and I can take minus x1 prime and substitute x1 prime from the first equation. If I do that, x2 double prime becomes minus the right-hand side of the first equation. But also, this equation now contains two x2s and one x1. But what I know about x1 from my original second equation is that x1 is the same thing as minus x2 prime, right, if I solve it for x1. And therefore I can take x1 equal to minus x2 prime and replace x1 here by minus x2 prime. And if I do that, what is left is a guy like this, which is a second order ODE, but now it only has x2 in it, right? So there is no x1 left, so I have a single second order ODE as a result. I had a system in the beginning. At the end, I just get a single second order ODE. And in fact, this is a second order linear homogeneous ODE with constant coefficients once I move everything that was on the right to the left. So I can solve this second order ODE for x2. And once I solve it for x2, then I can find x1 simply by taking the derivative of x2, and that will give me x1. And what I would encourage you to do is to try to recover, right? So I solved this initial value problem already. But the question is, can I reformulate now this initial value problem in terms of this second order equation? So would I be able to derive the initial conditions from x2 for x2 from these initial conditions that I see here? And that actually is very easy to do, right? Because what these initial conditions mean, they mean that x1 of 0 is 1 and x2 of 0 should be 2. So if we take that and move it down here, and now what do we see? We see that for x2, I already got the initial condition, right? So I can just take that and add it here. So this is the initial condition for x2. And if I want to solve the initial value problem, I also need the initial condition for x2 prime at 0, right? And the only thing that I have is x1 of x0. But from here, we know that x2 prime is minus x1, right? So when when t is equal to 0, and then x2 prime is equal to minus x1 of 0, but x1 of 0 is 1. So x2 prime of 0 is minus 1. So the initial value problem for this system, for this vector value problem, can be in fact rewritten as the initial value problem for just a second order equation. So that means that regardless how you look at it, either you have two equations, two first order equations, on one second order equation. These things are equivalent because they involve the same number of derivatives somehow. All right, and next time we're going to discuss how we will be able to find the solutions out of which we can construct general solutions of systems of ODEs.